don't blink. That dark plume forming behind. The tail isn't a malfunction, it's the moment a machine wakes up. In front of you is the Lockheed Martin F-22 Raptor, one of the most advanced fifth-generation fighters ever built. And what you're seeing right now is not just a startup. It's a carefully engineered sequence, designed for speed, independence, and combat readiness. At the heart of this process is the APU, or Auxiliary Power Unit. Before the main engines even come alive, the APU supplies electrical power and compressed air to the aircraft. That means the jet doesn't rely on ground support equipment to get moving. In real-world scenarios, this saves critical minutes, allowing rapid deployment when timing is everything. As systems come online, the ground crew steps in, not with tools, but with precision hand signals. Every gesture communicates directly with the pilot. Control surfaces begin to move, leading-edge flaps adjust, ailerons respond, and the twin vertical stabilizers shift in perfect synchronization. This isn't random motion, it's a full systems check of the fly-by-wire control architecture, ensuring every input translates into exact aerodynamic response. Meanwhile, another crew member completes a final walk-around, checking landing gear integrity, exhaust nozzles, and tire condition. Every detail matters. At these speeds, even the smallest fault can become critical. Clearance given, the Raptor begins to roll. As it taxis out, the aircraft transitions from a grounded system to a fully independent combat platform. Then comes the moment, throttle forward. Afterburners ignite, twin engines unleash raw thrust, and within seconds, the jet surges forward and lifts off. No hesitation, no wasted motion, just pure acceleration. Once airborne, the performance shifts from power to precision. The pilot pushes into a steep climb, almost vertical. This is where the F-22 separates itself from conventional fighters. Thanks to thrust vectoring, the engine nozzles can redirect exhaust flow, giving the aircraft control even beyond traditional aerodynamic limits. Now the real demonstration begins. High G turns snap the aircraft across the sky. Rapid directional changes test both the pilot's endurance and the structural limits of the airframe. At supersonic speeds, the jet executes aggressive reversals, maneuvers that demand both strength and computational precision from onboard systems. Then comes controlled instability. The aircraft enters a descending rotation. What looks like a loss of control is actually a managed aerodynamic state. Using thrust vectoring and real-time flight control corrections, the jet stabilizes itself mid-descent and transitions smoothly back into controlled flight. Moments later, the Raptor slows dramatically, nose pitched high, almost hovering. This is high angle of attack flight, where traditional lift is minimal. Yet the aircraft maintains stability, balancing thrust and airflow with extreme precision. This is not just maneuverability,